Second thing I'm going to do is share my screen via cable. And share my files right here. And this is 2 p.m., so we're 11 a.m. So we're at the end. So let me move this thing and extend my screen. Let me go make sure that there is the chat open. All right, there's the chat there. And there's our screen as big as it gets. All right. Okay, so we're going to get back and finish up chapter 2 today, and then we're going to start chapter 3. Chapter 2 is all about functional groups. And I told you the great thing about having IR at the end of our first chapter of 2 is that it shows you that those different functional groups have different types of bonds. And those different types of bonds have different energies, and we can see that they have different energies by looking at them on the IR. So these bonds will absorb different kinds of energy, and therefore these heavy light atoms absorb higher energy, higher frequency, higher wave number light. And then the triple bonds, the double bonds, and the single bonds. So know the zones where each of these different types go. Okay, that's going to be very important to Wednesday's quiz and as we go further on and on. Okay, so questions about this zone and or chart. So bond equals energy, frequency of light equals energy. Triple bonds have more vibration than a double bond than a single bond. Okay, so that being said, we looked at some hydrocarbons, and we started out with just sp3 hybridized carbons, and they all had carbon-hydrogen bonds just below 3,000. Then we moved it a little bit and said, hey, we have a hydrogen on an sp2 hybridized carbon, and we can distinguish that from a carbon with an sp3 hybridized carbon because those peaks are just above 3,000, okay? So we go from having that peak to, I'm gonna change color here, to having right here at this 3,000 line, the ones below it are the sp3 hybridized carbons with hydrogens on them. The ones above them are the sp2 hybridized carbons with hydrogen on them. Notice I said it has to have hydrogen there. If you have a double bond in the middle of a chain that has no hydrogens on it, then it will not show up there. Okay, so you have to have that hydrogen. That's the carbon-hydrogen frequency. And then we saw that when you do something with aromatic rings, you see you have a single bond, a double bond. And in this case here, you have a methyl group with the sp3 hybridized carbon. So it has things below 3,000. And then we saw that these were the sp2s, and so they had things above 3,000. And so we should see something in the carbon-carbon double bond range as well, which is between 1,500 and 2,000 wave numbers. And we do see that. In fact, we see these crazy little things called combination bands. And I told you that aromatic ring wasn't exactly a single bond alternating double bond single. So it's not 3 double bonds and it's not 3 single bonds. That's why we get this weird pattern. Okay, so we have that very common pattern, but we also have a nice peak here from our carbon-carbon bond, a nice clear peak that is our carbon-carbon double bond. And then we'll have some carbon-carbon single bonds down here as well. So we've gone from our hydrocarbon with only sp3s, at our carbon hydrogens all below 3,000. We started with an sp2 and saw that was just above 3,000. What if we turned it into an alkyne? And not only an alkyne, but it has to be an alkyne with a hydrogen on it. That alkyne carbon is sp hybridized, which means, is it going to go above 3,000 or below 3,000? Above, because sp3 is just below, sp2 is just above, and so it's going to be just a little bit more. Remember when we were talking about hybridization, sp3 has an S spread out over 4 orbitals, 25% S. The sp2 is an s orbital spread out over 3 equal orbitals, 1/3 S. sp orbital is 1s over 2 orbitals, so it's 1/2 S. And so that's why it keeps marching up to higher and higher frequency. Okay, so again, you have to have the hydrogen there to see it. And so if we draw our line at 3000 right here, like 3000 to 3200, that's probably where we're going to see our sp2s. And notice this is right up here at 3300. 3300. And it's nice and sharp, as a lot of our carbon hydrogen peaks are. But then if we go down into our range, we go down to our 2500 to 2000 range, we have a peak there. That's the first time we've had a peak there. That's our carbon-carbon triple bond. Only 3 things show up there. In this class, only 2 things show up there. Carbon-nitrogen triple bond and a carbon-carbon triple bond. And then we have really nothing down here. This is a fairly weak peak here until we get below 1500. And then all this is our carbon-carbon single bonds and our carbon-hydrogen wags and wiggles and stuff like that. So we only see this hydrogen if it is on the end of the chain. If that alkyne is in the middle of the thing, we do not see this peak. We still see this peak, and the intensity of that peak increases the less symmetrical that alkyne is. So in here, we have a carbon on one side. Over here, we have a carbon on this side and a hydrogen on this side. Therefore, it's a little polar, and it's going to be a little stronger than if you had a carbon on both sides. Because it's less symmetrical, I mean, because when it's more symmetrical, it's less polar, less intense. Okay. All right, questions about our hydrocarbons, seeing that our carbon-hydrogen peaks change, as well as our carbon-carbon single bond, carbon-carbon double bond, and carbon-carbon triple bond. Okay, so now let's transfer to another functional group here. And we're going to go to the second thing that absorbs in that high level between 3000 and 4000 wave number. And it's the OH. So when we have an alcohol, the carbon, oxygen, hydrogen bond, alcohol functionality, we have an opportunity for that hydrogen to hydrogen bond. So number one, it's a heavy atom, light atom, so high energy. It hydrogen bonds in a bunch of different ways, so it broadens the peak out. And the carbon-oxygen bond is a polar bond. And we actually see those down here. These are carbon-oxygen bonds down here, single bond. But we see the oxygen-hydrogen bond up here as being very intense because that's a polar bond. It's broad because of hydrogen bonding. It's intense because of the polarity of the bond. Now, in this particular one, if we draw our line here at 3000 again, it looks like we only have sp3 hybridized hydrogens right here. And if we look at our structure, our condensed structure for 2-butanol, we see only that. So we shouldn't see anything in the triple bond range. So we don't see anything here. We don't see anything in the double bond range. We do see some in the carbon-carbon bond range and the carbon-oxygen bond range. And then, of course, the wagging and wiggles. Notice there's a lot of peaks down here. The fingerprint peak, the fingerprint region, usually will have a lot of those peaks. Questions on this alcohol. So in our functional groups, as we talked about, and we went from that alcohol, which is the carbon-oxygen-hydrogen peak functionality, to going to a carbon-oxygen-carbon peak, and it changed names. It turned into an ether. So structurally, it's different. And if we did that, what happens is that OH peak goes away. All those other peaks are still there. We still have our hydrocarbon peaks right below 3000. We have nothing between 2500, 2000, or 1500. And we only see that carbon-oxygen bond, and it's probably the intense one, because it's more polar bond than a carbon-carbon single bond. So this is probably the carbon-oxygen single bond being very intense and below 1500. Questions on that? So that means if you were in the lab and you started with an alcohol and you wanted to make an ether, you actually want to look for this change to happen. The OH peak goes away. And you get this even more intense peak in that carbon-oxygen single bond range. All right, questions on that? Okay. So again, these are strong absorptions because they're polar bonds. Okay, so let's get into nitrogen, okay? Nitrogen was that third thing that happens in that high range between 3,000 and 4,000 wave numbers, okay? Nitrogen, hydrogen. If there's a hydrogen on a nitrogen, it will show up there. And because it does hydrogen bond, it's going to be slightly broad. But it's less polar than the oxygen hydrogen bond because they have closer electronegativity. So it's less intense than the oxygen hydrogen bond. So we see a less intense. And because it hydrogen bonds, we see a slightly broadened peak. So if we look at this, we have two peaks here. Nitrogen's really clever because if you have two hydrogens on nitrogen, you're going to have two peaks. If you have one hydrogen on nitrogen, you're going to have one peak. If you have 0 hydrogens on nitrogen, you're going to have 0 peaks. So that tells you, number one, whether you have a primary, secondary, or tertiary, meaning immediately upon looking at the 3,000 to 4,000 wave number zone of the IR. But then let's look what we have here. So we're going to draw our 3,000 peak again. Let's do here. Our 3,000 is going to be right here. So that means this is probably the carbon hydrogen peaks here. These are probably the aliphatics for this. We have a combination peak. We have a peak right here. This one right here is probably the carbon-carbon double bond because we see that in the aromatic ring. And then we have below 1500, the carbon-nitrogen bond, which is polar. So we see it as fairly intense. But notice we don't have anything in the triple bond range. We do have these smaller sets of peaks. So we can identify each of those peaks in each of those zones and say, oh, yeah, 2 hydrogens here. So that makes sense to have 2 bonds here. Benzene rings are going to have above 3,000. Methyl group below 3,000. We're going to have carbon-carbon double bonds. And then we're going to have stuff below 1,500. You can identify each and every of these groups in this spectrum. Questions on that? Yes.
What was the really large peak by 1,500?
The really large peak by 1,500, this one right here, because it's right above 1,500, I'm going to call it a carbon-carbon double bond.
Is that what the one to the left was?
This one's also a carbon-carbon double bond, and then this is one of those combination bands. If there's up to 4 that happen there.
What would separate those, make them different frequencies?
Well, because the carbon bond over here next to the nitrogen might be a little different than the carbon-carbon double bond next to the methyl group. So there's another reason, but it's beyond the scope of this class. But that'll explain it well. Okay. All right. So that means we have our amines taken care of. So that's everything that has those high ranges, right? Everything that has those high ranges, carbon hydrogen bonds, oxygen hydrogen bonds, and nitrogen hydrogen bonds. We can identify them each by their different shape, and we can tell how many hydrogens are on the nitrogen because of how many peaks show up. All right, so moving right along, we already did the carbon-carbon triple bond. It's one of the 2 things that show up between 2,000 and 2,500 wave numbers. The other one is the carbon-nitrogen triple bond, or the nitrile. So, wow, we've already gone through a whole bunch of our functional groups already, right? We went through our hydrocarbon, our alkene, our alkyne, our alcohol, our ether, our amines, and now we're hitting our nitrile too. So every single functional group we talked about, we can identify that bond type by IR. Okay, so they aren't mythical, they do exist, and this is my proof. Okay, so in this range here, again, we only have aliphatics right here. So there's a long aliphatic chain. So these are below 3,000. The only thing in that range, and then nothing else happens until below 1,500. Carbon, single bonds, and carbon-hydrogen flags. All right, so that's really nice that it gives a very clean spectrum. Okay, so now let's talk about the carbonyl group. Okay, the carbonyl group, remember, is the beginning of a whole family. We started with the carbonyl that was attached to a hydrogen as the aldehyde family. Then we said 2 carbons attached to it. That's the ketone family. A carbon and an OH, that was the carboxylic acid family. And then we can change it by taking the H off and turning it into an ester, or taking the O off and turning it into an amide. Okay. But the key feature in all of these is the fact that you have the carbonyl. The carbonyl is a polar bond, 2 bonds between carbon and oxygen, and therefore it has to be between 1,500 and 2,000. And because it's a permanent, strong polar bond, it's always intense. Okay, the only thing that changes is when you put stuff near it, it'll shift it back and forth a little bit. So if we look at our aldehyde here, it's centered right around 1,700. Okay, that's the hydrogen. It's about the same nucleophilicity, electrophilicity. Sorry, it has about the same electronegativity as carbon, and so there's not really. So that's kind of the center point. If we look at a carbon-carbon, again, it's kind of centered right around that 1,700. Maybe shift a little higher. So the electronegativity of hydrogen and the electronegativity of carbon are about the same. And therefore, it's not going to shift that O double bond C very far. But now let's put a oxygen there. And if you think about those oxygens with those 2 lone pairs right here, it actually goes way above 1,700. It's always above 1,700, really close to 1,750. So we have an electron donating group. We have a more polar bond here, shifting us to higher frequency, higher energy. Okay. Now, if we take the OH here, the OH can hydrogen bond, and so it can shift even higher, 1,780. That's almost 1,800. Okay, but it varies quite a bit because of how it can hydrogen bond. Now let's go to the amide right here. Nitrogen is closer in electronegativity than oxygen to carbon, and it now shifts it just below the 1,700. It only has the 1 lone pair, and so it's below 1,700. The oxygens with the bigger lone pair is above 1,700, almost 1,750. So you can watch the carbonyl change its electronegativity, what's bonded to it, by following its trend going above or below 1,700, and knowing that the amide is going to give you below 1,700. The carboxylic acids and esters are always above 1,700, and your aldehydes and ketones right at that middle point. Okay, questions on that? No questions in the chat. All right, so what does this look like? Well, like I said, it's a very polar bond. And so you're going to have a very strong absorption. Almost always, if you have a carbonyl, it's almost always the strongest absorber. Okay, so let's kind of get a little bit into teach mode here and go, okay, we're traveling along, nothing's absorbing, maybe a little impurity on the glass is absorbing something. Nothing happens. Oh, we have some sp3 hybridized carbon-hydrogen bonds, and we have our absorption for those. Okay, so that's this right here and this right here. And then we have no double bonds, no triple bonds, so nothing's absorbing until you get to your carbonyl with your very strong absorption, and then nothing absorbs until after 1,500. And now we're looking at our carbon-oxygen single bonds, carbon-carbon single bonds, and carbon-hydrogen flags. Okay. But do you see how intense that peak is? And if we look at this one, It's centered right on 1700. So it's probably an aldehyde or a ketone, right on 1700. Okay, so if we move on to, I don't have an example of an aldehyde here, but aldehyde also has a very specific peak. And I'll show you why. We have the carbon, hydrogen, and then this is a carbon over here, right? So this peak right here should show up at the high end range, right? Should show up between 2,500 and 4,000 because it's a carbon-hydrogen bond. But it's a carbonyl, which makes it kind of weird. And it actually shows up right here at 2750. If you have an aldehyde, this carbon-hydrogen bond will show up at 2750. Nice little sharp peak. So that's how you can tell the difference between an aldehyde and a ketone. If all you have is your carbonyl peak at 1700, and you're saying, well, there's an aldehyde peak. Well, the aldehyde will have that peak at 2750. The ketone will not. Okay. I just want to give you a little bit extra on that one. Okay, so if we go to carboxylic acids, think about alcohol, right? We had something that hydrogen bonded, and so it gave a broad range, okay? So now we have something that hydrogen bonds, but it can hydrogen bond to both the carbonyl oxygen and its own oxygen, so that is going to broaden it out even more. So what we see is a characteristic peak where if you had just OH, you would have a peak above 3,000. But, okay, let me change that to, yeah, there we go. You'd have your OH peak for an alcohol would be above 3,000. But when you have the carboxylic acid, it does something really strange. It actually absorbs broader and all the way across that 3,000 range. So it absorbs from 2,500 to 3,500 in the biggest, broadest hydrogen bonding peak you'll see. What that means is that that's going to obscure your carbon hydrogen peak sometimes because it's over that range. But now we have our carbonyl peak, which is our next strongest peak. It's about 1750. It's not at 1700, it's almost at 1800. So these two peaks, this broad peak here and this carbonyl stretch tells us we have the carboxylic acid. We have the broad peak above 3,000, it's an alcohol. We have the broad peak over 3,000 and a carbonyl, we have a carboxylic acid. What if we took this and changed it to an ester from the carboxylic acid? This big peak goes away, but the carbonyl should stay and stay pretty close to the same zone. So if we started with an ester, we would see this peak maybe shift a little bit, but this go back to having your normal sp3 hybridized hydrogen. Okay, questions on that? So this big old peak over 3,000 is very representative of carboxylic acid. It might show up on a quiz sometime. Okay, so if we look at our amides are the same as amines. If you have one hydrogen on there, you're gonna have one peak. If you have two hydrogens, you're gonna have two peaks. If you have zero hydrogens, you're gonna have zero peaks. So in this case here, we have a nitrogen with two hydrogens on it. We can tell that immediately because of our our nitrogen hydrogen peaks above 3,000. So we have our 3,000 mark right here. Oops, a little bit lower. And we have two peaks, so that means we have two hydrogens on there. And then we see nothing else. Well, we see our sp3 hybridized carbon hydrogens. And nothing else do we see our carbonyl. But look where it is. This is, let's see, 1,600. This is 1,700. This is 1,800. It's below 1,700. 1,650. Because that's 15, that's 16, that's 17. So it's below that. So that's another indication we have a carbonyl compound bonded to a nitrogen because it's below 1,700. So we have two different zones to pay attention to when we're looking for what kind of carbonyl derivative we have. We can look at the top end or the bottom end and get additional information. Now, I said before, these peaks don't tell us the functional group. These peaks In any one peak just tells you what kind of bond it is. The fact that you have this plus this means that you can say, yes, I do have this structure. They all have to agree. If you have a functional, you have a double bond or something in your structure that you've drawn and it doesn't show up in your IR, try again, okay? Or if there is one in there, you got to figure out a place to put it. So you want to have all the different types of bonds represented in whatever structure you end up with at the end. Questions? Yes. Yes. No. The question is the peak at 3000 right here. That's just above. These are the sp3 hybridized carbon hydrogens because they're just below 3000, but they're above 2500. And our carbonyls are always between 1500 and 2000. And then our triple bonds are between 2000 and 2500. So knowing those zones, knowing where they are is very important. All right, any questions in the chat? Okay, well, so what I'm going to do now is I'm going to shift over to our chapter 3 slides. I posted those today. I've also posted the full slides for chapter 1, and I'll be posting the full slides for chapter 2 today. So go back, double check, make sure I wrote everything down on those things, and we can do that. So let's see, I want to go to eliminate. All right, so now on the quiz, if you were live in person, you would have noticed that there's a question on there that you would have done a lot better if you've done the homework. So please go look at the homework assignments and have those done before the quiz. It'll help you. Okay, specifically question number 8, the draw the structures. That was at least 2 questions in the homework. So that would have been really helpful. Okay, so I'm going to tell you an inside secret. This isn't in the slides, so you got to write it down. There is a secret that I have not shown you in these slides. Yeah, I haven't shown you in these slides, but it's on the Canvas site. There's only 5 things that can happen in a mechanism in this class. Until we get to radicals, you can only do 5 things. We're going to look at those right here, and they're not going to be numbered directly, but I'm going to show you. You can add a proton. So that means we're going to talk about acids. You're going to take away a proton. That means we're going to talk about bases. You're going to attack a nucleophile with an electrophile. So something with a partially positive charge is going to attack something with a partially negative charge. Or something with a full negative charge is going to attack something with a full positive charge. So that's number 3. Add a proton. Take away a proton. Attack something that is charged with the opposite charge. Break something apart to form a stable radical or ion. And the last one, number 5, is rearrangement. So at rearrangement, we can rearrange the molecule. We're going to see every one of those examples in today's lecture. I just wanted to give you a heads up that those are the 5 things you should look for. Mechanisms are not weird and crazy. They do one of 5 things. Follow along. If it's in an acid catalyzed, you're going to add a proton. If it's base catalyzed, you're going to take away a proton. If you only have positive and negative charges, those are probably going to react. If it can break apart to form a stable or an intermediate or something, it might do that. And if it can rearrange, it could do that as well. So those are the only 5 things you can do. In fact, on Canvas, there's a thing in resources, the top one on the list called the 5 things that can happen in a mechanism. Download that. Do not tattoo it on your arm, but you know, we don't want to cheat on a test, but you know, it'll be fun. Okay, so I want to show you that most organic chemists are lazy, but tell you a whole bunch of information by the way they write things on the screen, okay? So usually we're talking about a reaction where we have an arrow going from what you start with to where you're going. Now, it could be the intermediate or it could be something else, but usually these reactions are drawn with starting from the left side of the board going to the right side of the board. That's not always true. Sometimes they'll go down. Sometimes we'll do a thing where we actually go in a spiral pattern, but what we want to see is the direction the arrow is going. The direction the arrow is going means it's going from this compound to this compound. And usually that it takes something to make that change. So the thing you're doing the reaction on is typically called the substrate. Okay, it's the thing that is being reacted. The thing making the change is the reagent. So the reagent is the chemical structure that reacts with the substrate to make it something that it changes to. And then what we do is we can draw an arrow that says that. But again, we want to give you as much information as possible. So sometimes we're going to write down solvent because that's going to change the mechanism. Sometimes we'll write down temperature or pressure or whether or not light is involved or whether or not another reagent was involved or there are multiple steps. So we'll show you all of those things in your reactions and you can follow along with that as it goes. So the idea here is that we are going to give you as much information as you need to draw a logical conclusion from what is going to happen. So let's start with something like this. So that's a really bad alkene, but it is an alkene. So we have a double bond here. We have a ring of 6 carbons. Okay, so I'm going to call that the substrate because that's what we're going to react to change. Okay, so then we're going to draw an arrow over here. And I'm going to say we have bromine here. Now, in this case, if there's only one thing on above or below the arrow, that's typically the reagent. Okay, and then we can say, okay, well, that's going to go and do some reaction. We don't know exactly what this reaction is yet, but we're going to say that that is our product. Again, we're not losing a carbon here. We're just, let me clean that up. It's still 6 carbons in a ring, but we've changed from a double bond between 2 carbons to 2 single bonds with bromine. So what has happened here? Well, we've done a reaction. Substrate, reagent, product. And it goes from substrate to product by the air. Okay, so we're telling you where we want your mind to go, okay? So, but that might not be the only way to do it. Sometimes we might say, oh, you know, instead of doing the reaction the way it's written here, let's give you even more information. Let's say we're going to do it in bromine, but we're going to do it in the presence of light, and we're going to do it with heat. Little delta, little triangle there would be heat. H nu is light. Bromine is still the reagent. If I give you additional information, that's going to say, hey, maybe it's not the same mechanism as this. Maybe it's going to react some other way. Okay, and so we might end up with something that is going to look like this. Don't know why yet it's going to do that, but I've given you information and told you the product's different. So are these the same mechanism, the top one and the bottom one? No. Are we going to learn these mechanisms? Yes. Okay. The other thing we need to think about is if we have a reagent that we're working with, and we have a line, and then we have numbers, 1 and then 2, and then we have some reagent up here, and then some reagent down here. What this means is that you react the substrate with reagent number 1 first. After it's done reacting, you react it with reagent number 2. Usually there would be an intermediate there, but if you normally always do that second part of the reaction, then you can say, oh, well, it actually did react to give me my final product over here. So the 1 means the first reagent until it's completely reacted. The 2 means the second reagent until completely reacted, and you only have to draw the product of both reactions. All right, questions on that? Now, a lot of times there's side products or things given off like HBr or stuff like that. If it's not the organic compound, we typically ignore it. We'll write it for a mechanism so you'll see where it went, but we typically don't write this, the inorganic product in the system. All right, questions on that? All right, so let's move on. So if we react, if that's a reaction, that just shows you what's changing in the system. What's a mechanism? Well, a mechanism is basically a logical construct to tell you how you got from A to B. Again, it's not magic. There's things that happen. There's only 5 things that can happen. So those 5 things have to happen in your mechanism, okay? So the mechanism really tells you how the bonds were breaking and making to go from your starting materials to your product. And it usually goes in a specific order, okay? So if it happens all at once, if it goes from starting material to product all at once without generating some kind of intermediate, we call that a concerted reaction. Concerted reaction. It happens all in one step. And so imagine you just have compound A going to compound B, and then compound B is your final product. Boom, done. Okay. So that means you had some bond making or breaking happening all at the same time to give you your product. Concerted reaction in concert. In concert happens all at once. But a lot of times we also have things where it goes from A to some intermediate compound, then it goes to B, okay? Usually the intermediate is some high energy material. It has more energy in it than the starting material of the product, and it wants to react very quickly, but it had to be created first before you can make your product. So that's what we call a stepwise reaction, and you always generate some intermediate in a stepwise reaction. All right, questions on that? Okay, so this is just how we can describe the 2 different types of mechanisms. Let's talk about some of the notations we'll use, okay? When we're talking about these mechanisms, we're going to use arrows to show where the electrons are flowing. So you're always going to go from electrons to a bond or from a bond to form electrons. So you're looking for where the electrons are flowing, okay? If 2 electrons move at the same time, we're going to use a curved double arrow, 2 prongs on that arrow. Notice that we're using a curved arrow here. If it's a straight arrow in one direction, that's a reaction. If it's a curved arrow with 2 prongs on it, we're moving 2 electrons. And if we have a reaction that has 2 arrows that are opposing, we call that an equilibrium reaction. And if you think about it, the top one means the reaction was going in that direction first, but there's something that it can react with to make it go back in that other direction. So by having this arrow look like that, that's telling us we have a reaction that can go forward or reverse and probably stop somewhere in the middle. We call that equilibrium. Okay? So curved arrow with 2 prongs is a pair of electrons, 2 electrons moving around. Okay, so how can we represent all of these things? Okay, so let's go with something we know, H. And this is just some acid here. In fact, I'm going to change it to an A to show you it's an acid. A, right here. And then we're going to react that with something B. And we're going to say that goes. And then we're going to say, because acids and bases sometimes will react with equilibrium. So I'm going to tell you there's an equilibrium here. It's going to go back and forth. But now we have to use those curved arrows to show what's happening. Okay, so if we're going to show curved arrows here, what's going to happen is these electrons have to come over here and grab onto that hydrogen. Because right, we're having an acid-base reaction. Acid-base reaction means we have to transfer a proton. So we're transferring a proton. What happens with these electrons? These electrons stay on the more electrophilic atom. So what does our product look like? Our product looks like A with a negative charge because it has all those electrons around it, 8 electrons there, plus B hydrogen. What happened to that lone pair of electrons on the base? They became the new bond with hydrogen. Remember, the bond right here, that one line is 2 electrons. So these 2 electrons became the new bond between the H and the B. Okay, do we see how that happened? And we're showing the electrons flowing with the curved double arrows. Okay, all right, let's see. So to review, the reaction arrow is drawn in just one way, that way. It tells what you started with is on the non-arrow side, what you ended up with is on the arrow side, okay? The double arrow means that it can go in both directions in the reaction. The double-headed arrow that we drew when we had resonance structures. Remember, resonance structure is not going back and forth between those two. Neither one perfectly represents what it is, so it's somewhere in between. It's somewhere in the hybrid system. So that's our double-headed arrow. Then we have our full-headed curved arrow, and then it has to be curved if we're moving 2 electrons. And if we're moving just 1 electron, it's going to have 1 little arrow. And we will do that in chapter 10, where we only move 1 arrow, 1 electron. But for the most of the mechanisms we're going to start with, we're going to be moving 2 electrons. So you want 2 prongs on your arrow when you're moving electrons. When you're moving electrons, it's a curved arrow. Okay, so we have 5 different arrows that we can play with. Straight arrow for reactants, double-sided arrow, double arrows going both directions for equilibrium. Double-sided double arrow is resonance, and then our curved arrows to move electrons. Questions on that? All right, great. So now we know what we're going to look for when we look for our mechanisms, right? So the thing we want to make sure when we're doing our mechanism is we're describing where the electrons are going, okay? So it could be the electrons in a double bond that are going somewhere else. It could be the lone pair going somewhere else. It could be a bond between 2 things that are going somewhere else. We want to show where those electrons have gone. So we want to show that flow of electrons in their thing, okay? So we want to start from where the electrons are to where they are being attracted to, okay? And always show your electrons flowing from the higher electron density side. So think lone pairs, double bonds, more electronegative atom, and never show movements of atoms, because again, all we want to do is see where the electrons are moving. Our curved arrow is only about electrons. So if we were to demonstrate that, we would have something like, well, let's go with this right here. This OH group has a negative charge on it. This hydrogen has a positive charge on it. So what we're going to do is we're going to say, oh, these electrons are going to come over here to form a new bond with that hydrogen. So the electrons are coming from the oxygen. Are there electrons that we can use to go in that direction? No, there are no electrons on that hydrogen to do that reaction. So we can't do that. We cannot do that. Okay. So what would that look like in more of an organic type reaction? Let's not do 5 bonds to carbon. That's already -1 on the quiz. So we're going to do, let's do an H there and a CH3 there. And let's put our lone pair up here, just make sure that we Noted it there. And let's do a nitrogen down here with 3 CH3s on it. CH3. Okay, so these aren't going to react at all, right? Well, let's draw some electrons. We got a lone pair here. Oh, wait, hold it. We have a partially positive charge here and a partially negative charge up here. Ooh, I know what's going to happen now. I'm going to move those electrons to the thing that's more partially positive, right? So we're going to move these electrons in that direction there. So now I know what electrons are going to react and where they're going to react on the other compound. Just by playing around with those electrons, just by forcing those electrons around, you can see what's going to happen. Okay, questions on that? Okay, well, let's do one more because it's in my examples. H and CH3. And then if we have OH, and again, we have those lone pairs on the oxygen here, and it's negative here. What we're going to see is one of those lone pairs is going to reach out and make a new bond with that hydrogen. Curved arrow, 2 electrons reaching out. But what happens to this bond? Hydrogen can't have 2 bonds. So that means these electrons are going to go onto the oxygen and give us a negative charge. So that means our net reaction is going to be, after our electrons have all moved, we have a negative charge on here and HOH over there. All right, do you see why you always track your electrons? You go from the electrons to forming a bond. But notice here, we use that bond and we made them back into a pair of electrons. When a new bond was formed on the hydrogen on this side, we had to break this other bond. Those 2 electrons in that bond became a lone pair. Does that make sense? Bonds are always 2 electrons. A pi bond is 2 electrons, a sigma bond is 2 electrons, and we're always going to see this kind of exchange back. All right, questions on that? Okay, so that being said, we're going to cover the 4 most common reactions we'll see in this in organic chemistry. We have a couple more next semester, but this will cover most of them. The first one is what we call a substitution reaction, which what you might think it is. You take something off the compound and you put something on. So you've changed the bond between the substrate, the carbon containing thing, and something else. The next thing we have is an addition. In an addition, what we're going to do is probably going to take a double bond and add something across it. Pretty straightforward, right? Then we're going to do an elimination, okay? There's a couple different ways we can do eliminations. We can eliminate 2 sigma bonds and get a pi bond. Or we can eliminate a sigma bond and break into a charged species. Remember, there's 5 things we can do, and that's one of them, break apart to form something. And then the last thing is rearrangement, okay? So that's the last kind of reaction we're gonna have. So if we think about just substitution reactions, what we're looking at is a simple changeover from CH3, Cl. We're going to react it with OH, negative, which those are where the electrons are. So in my mind, these electrons are going to come over here, react with the carbon. These electrons are going to leave with the chlorine to give us H3COH plus chlorine minus. You say, hey, but Dr. Irvin, I've never seen that reaction before. How do you know that the OH is going to attack the carbon? Well, chlorine is more electronegative than carbon. That makes this the partially positive side, this the partially negative side. These electrons are going to attack the partially positive side. So we have our substitution reaction. Just by knowing bond polarity and where the electrons are, we know our first reaction, our substitution reaction. We've substituted the chlorine for OH to generate our product, okay? We can also do that in a couple different ways. Okay, so now we have this 1, 2, 3, 4 carbons right here. we have bromine, but I have that H nu on there telling you that we're actually going to use light. And what it ends up doing is, oh, sorry, it's bromine too. We're going to replace that hydrogen with a bromine and generate HBr. So what's substituted here? The hydrogen has been substituted by a bromine. Substitution reaction. And one of the last ones we're not going to do this semester, but we'll do next semester, is we're going to take a hydrogen off a benzene ring and substitute it with a chloride. So anytime you are substituting one thing for another, and it has the same number of sigma bonds at the end that it started with, it's probably a substitution reaction. Questions on substitution reactions? Okay, so that means that our next set of reactions are called addition reactions. In addition reactions, you usually have at least one pi bond. And so what you'll end up with is you'll start with two compounds and you'll end up with one compound. So let's look at this right here, CH3, H. And we're going to react that with bromine again. And we're going to add the bromine across the double bond, giving us our final product with two bromines on it, bromine here, CH3 group, and then a hydrogen, and hydrogen. Okay, so we started with two different compounds, and we ended up with one compound. We added them across the double bond, addition reaction. Substitution, we had two things, we ended up with two things. Addition reaction, we started with two things, we ended up with one. Okay, so that means that if we have elimination reactions, we start with one thing and we end up with two. So let's do something like, let's see, not there. Elimination reactions. So we're going to start with, oh, not a double bond. We're going to start with a bromine and a hydrogen already on our compound right here. And we're going to remove it right here. So an elimination reaction is turning one compound into two. It's a plus. So whenever you break a compound apart, imagine anytime you take two sigma bonds away and turn it into a pi bond, you are doing an elimination. Okay. So then our last thing we can do here is rearrangement. And so what we'll see here, and I'm going to draw it in stick figure. If we have a compound that looks like this, and we do something to it, or it self-rearranges, it can, if it moves from one compound to another, we've changed the skeleton of the carbon backbone, it has rearranged. It has gone from the methyl group being over here on the number 2 carbon to the methyl group being over here on the 3 carbon. And that's rearrangement. And we can draw it. Okay, so substitution, elimination, addition, and rearrangement. Okay, questions on that? Okay, so let's see, nothing in the chat. Let me do this one last thing. We'll start acids and bases on Wednesday. So when we think about this, we can only have 5 things to happen. Add a proton, take away a proton, break into a stable molecule, rearrange, or have something, a nucleophile react with an electrophile. Something partially positive react with something negative, etc. So how do we break these bonds? Well, there's a couple different ways to break a bond. And if we just have a carbon and something else, And in this case, Z is probably anything more electronegative. So it's going to take the electrons with it. Okay, there's a couple different ways it can break apart. Okay, the first way it can break apart is where the electronegativity difference between the carbon and the Z is not very high. Okay, so if it's not a polar bond, this bond is not very polar, it can break apart such that each component takes away one of those electrons in that bond. Your sigma bond has 2 electrons, it's breaking apart to give you 1 electron on each side. And we call that homolytic cleavage because they each leave with the same number of electrons. Homolytic cleavage. Homolytic cleavage. Now, if there's a big enough difference between the electronegativity between the carbon and the Z, then the Z wants the electrons more, usually. Okay? And what happens is we have both electrons go onto the Z, and we end up with the carbon, which now has a positive charge, and our Z that has a negative charge. We call this heterolytic cleavage, because the 2 components ended up with different amounts of electrons. Okay, so let's go back to those things we can do in a mechanism. We can break something up to form a stable ion or bond. So that's heterolytic cleavage or homolytic cleavage. But now here we have a positive and a negative charge. That means we can react something that's electrophilic with something that's nucleophilic, something that wants a negative charge or wants a positive charge. So by breaking those apart, we get to those different steps in the mechanism. All right, questions on that? Okay, we're going to stop here. We're going to start on acids and bases on Wednesday. We're also going to have a quiz on IR and the rest of chapter 2 on Wednesday, and then we should all be caught up for our quiz for the following week. We'll be on chapter 3. All right, thank you at home. If you have any questions, go ahead and say bye and put them in the chat. I'm going to go ahead and stop sharing and stop recording.